Hey everybody, this is Dr. Retzek. This is our fourth video here in 7a where we're talking about adjoints of linear maps, and we've kind of specified all the way down to adjoints of linear operators, and we're studying self-adjoint operators. So let's get started. This is a continuation in 7a. The setup for reference is we have an inner product space V. We have an operator T that takes inputs from V and produces outputs in V. And we know the adjoint in general is connected to the original operator T in this way. If you do the inner product of TV with W, that's the same as doing the inner product of V with T star W. So in that sense, T star acts right to left in that picture. Okay, what we want to do today is prove just a couple of theorems related to some of the work we were doing yesterday. Here's the first one. Theorem. Over C, T, a linear operator acting on V, is self-adjoint if and only if TV inner product V comes out real for all V in the space. So this theorem actually characterizes the operators that are self-adjoint. Remember, self-adjoint just means that T and T star are the same. So we know T and T star are the same over a complex vector space if and only if the inner product of TV with V comes out real for every V. This is not true for real inner product spaces, so the over C is important in this statement. And the proof is actually really quite nice. Here's the proof. For any V, we're interested in whether or not inner product TV with V is real. So we're going to look at the difference between that inner product and its complex conjugate. If that difference is 0, then the object must have been real in the first place. So check this out. Take any vector you want in big V. Now look at inner product of TV with V, take away its own conjugate. Okay, well, this is an inner product space, and so we have, conjugate symmetry, is that the word for it? So this is really TV inner product V, take away V inner product TV by conjugate symmetry. Of course, that second inner product, by the very definition of the adjoint, that's really T star V inner product V. Remember, that's how T and T star are related. You just flip them back and forth. First slot, second slot. And then we have additivity in the first slot. So this is really T minus T star acting on V, inner product V. Okay, and that has nothing to do with the hypotheses of this theorem. That's just a fact. It's just a fact that's just true. Okay. The question is, what kind of mileage can we get out of this fact? So let's suppose first, let's go in the forward direction first. So let's suppose T is self-adjoint. In other words, T equals T star. Well, look at that big display that we just wrote down, that string of equal signs. If T equals T star, look right here. That's 0 if T equals T star. So if T equals T star, then TV inner product V take away TV inner product V conjugate is 0. Thus, TV inner product V is real. All right, so we're done with that direction. All right, let's try the other direction. All right, here we go. Suppose that TV inner product V is real for all V in our inner product space. Okay, so now we're trying to argue that T must be self-adjoint. Okay, well again, look at this big display right here. That giant string of equal signs shows you that if TV inner product V is real, well then this side is 0. And if that side is 0, then the far right-hand side is 0. In other words, T minus T star acting on V, inner product V, equals 0 for all V in the vector space. Now we proved just yesterday that in a complex vector space, if an operator is such that TV is orthogonal to V for every V, then that operator is 0. I think 714 it was. T minus T star is 0. So T equals T star. Done. So zoom out. Look at what we proved. Over a complex inner product space, being self-adjoint is equivalent to inner product TV with V being real for all the vectors. So that's nice. That's how you end up self-adjoint over a complex inner product space. Again, not true for the reals. All right. Our second theorem follows up on the theorem we just used. The theorem we just used said, over a complex inner product space, if TV is orthogonal to V for all vectors, then T must be 0. Remember, that wasn't true for real inner product spaces. Our example was just rotation by 90 degrees, like say in R2. Okay, but if you add a hypothesis, then it is true. Second theorem. If T, linear operator on V, is self-adjoint, and TV ends up orthogonal to V for every vector in the inner product space, then T equals 0. Okay, hit pause for a sec here. This feels like a theorem we already know. Slightly different. Over the complex field, this theorem is already true without even the hypothesis that T is self-adjoint. Over the complex field, if TV ends up orthogonal to V for every vector, then T is 0. So the innovation here is that we got to drop the hypothesis that V was over the complex field, but we had to replace it with knowing that T was self-adjoint. Okay, so this is true even without T being self-adjoint if we were over a complex scalar field. This theorem says it's true over whatever the scalar field is, provided you know the operator is self-adjoint. Here's the proof. The proof actually, do you remember that crazy sort of technical out of nowhere fact from yesterday? The proof exploits that fact. For any U and W in the space, the inner product of TU with W, all right, remember that fact? It was like, what was that? We tried to write this as some big expression involving only inner products of T of stuff, comma stuff. Well, it's kind of the same here. So I think we're going to write T of U plus W, comma U plus W, take away inner product of T of U minus W, comma U minus W, all over 4. Yesterday there was a second piece where we had lots of I's running around. That piece, not available to us here because this theorem is conceivably true over the real field, so we don't want to assume that we have I to work with. That equal sign, this is true just by computation. Compute on the right-hand side, and when the dust settles, you just get TU inner product with W, where you're really using a couple facts there. You're using the fact that T is self-adjoint, so T is equal to T star, and you're using the fact, we may as well assume, can we assume over R? I think we should do that at the start of this proof. That's no loss of generality because the theorem's already true, even without the self-adjointness hypothesis, if we were over C. So let's assume that we're over R. There. Now I feel like the left side and the right side have to match, because over R, like say you had a W comma TU running around on the right-hand side, that's the same as TU comma W, because conjugate symmetry is for free over the reals. In any case, you guys FOIL out that right-hand side, and you will see that these are equal. Thus, if TV ends up orthogonal to V for all V, then TU comma W is 0 for all U and W in V. In particular, TU inner product Tu is 0 for all u in V. So Tu is equal to 0 for all u in V. So the proof kind of runs out the same as that technical proof from yesterday. It's just you gave up over the scalar field of complex numbers in exchange for this hypothesis. But the conclusion's the same. If TV ends up orthogonal to V for every V, then T must be 0. Okay. We're going to turn our attention next to what are called normal operators. And we're going to try to see how they're situated within the realm of all operators on V and whether normal implies self-adjoint or self-adjoint implies normal. We're going to try to get that all organized. But at least for now, we have a pretty decent handle on self-adjoint operators. They have real eigenvalues and they have kind of nice computational properties. All right, I'll see you next time. Bye.